All right, welcome. We're looking at section 2.3, which is the title of this section is the mathematical definition of a limit. But before we begin with that, I want to talk briefly about some notation. We can use absolute value and subtraction to find the distance between 2 points or two numbers on a number line. For example, what's the distance between 2 and 5? I know it's 3, but we can do that by subtracting and using the absolute value. So the absolute value of 5 minus 2 is 3. So that means the distance between 2 and 5 on the number line is 3. We can switch those numbers around and get the same result. So absolute value of 2 minus 5 is also 3. 2 minus 5 itself would be negative 3, but the absolute value makes that positive. So we're going to be talking a lot about distances as we go through this, and we're going to use absolute values and subtraction. So that's a key part of our definition. So that just means the distance between those two things, like the 5 and the 2, that distance is 3. Really more specifically, we're looking at when the distance is less than something, because we're trying to get really close. And so if we wanted to describe all the numbers x that were less than 4 units from 10 on the number line, we could say the absolute value of x minus 10 is less than 4. So this absolute value with the subtraction is saying the distance between these two numbers, x and 10, is less than 4. On a number line, that would look like this. Here's 10, and then if we go 4 units to the right, we get 14, and 4 units to the left, we get 6. And so I've got these dotted lines to say I'm not including those, but everything in between is less than 4 units away from 10. Also, we can do some algebra. We're going to have to do that today. And so algebraically, we could say the absolute value of x minus 10 is less than 4 is the same as saying x minus 10 is between positive 4 and negative 4. I'm just taking this 4 and making it positive and negative, and then putting this x minus 10 in between those two. If I want to get x by itself in the middle here, I can add 10 to all 3 places. So negative 4 plus 10, x minus 10 plus 10, and 4 plus 10. And then that's the same as 6 from negative 4 plus 10 is less than x is less than, where the 10s cancel, is less than 14. And that's the same thing we see on the number line. So that's a quick note as we begin about using absolute value and subtraction to talk about distance. Now, without any more previous stuff, let's jump into this formal definition of a limit. So we were looking at stuff with graphs and talking about as x gets close to c, the y values are getting close to something else. But getting close to, we really need a mathematical definition, so we don't have to use just our intuition to know what close to means. And so here we've decided, mathematicians before me have decided on this definition. So we're going to start with a function that's defined on an open interval. It's got some domain that contains this number c, where we're trying to get close to. And it doesn't have to be defined at c itself. It could be, it might not be. There might be a hole in the function or a vertical asymptote. But around c, it's defined. We say that the limit of f of x as x approaches c is L, and then we write it this way. This is the notation we looked at for section 2.2. Here's the definition. If for every number epsilon, that's a Greek letter, if for every number epsilon greater than 0, there is a number delta, another Greek letter, greater than 0, such that whenever the distance between f of x and L is less than epsilon, that's true whenever x satisfies that the distance between x and c is between 0 and delta. You might want to rewind that and hear me say it again. So I'm using absolute value and subtraction to talk about the distance. So I'm saying whenever a number x is between 0 and delta units away from c, then f of x is within epsilon units from L. And I can do that for any epsilon. that's the definition. Where do the epsilon and delta come from? They come from the French words that mean error, which also starts with E, and difference, which also starts with D. I think it's différence. Forgive my French pronunciation there. And so we're talking about little bits of error from L and little bits of differences from C there. Let me take you to a Desmos file where we can look at a particular example and I can try to make this definition make sense. So here I've got my function is a parabola negative 0.9 x squared plus 2, and I'm looking for the limit at c equals 0.5. Actually, let me show you this slide here. We've got the function negative 0.9 x squared plus 2, and I'm looking for what's happening, what's the limit as x approaches 0.5. So let me go back to my Desmos slide now. So as x approaches 0.5, this parabola, it looks like the y value is 1.775. This is a parabola, so there's not any holes or vertical asymptotes. And so I think the limit is 1.775. So I've got that hidden here for you. Yeah. So I think the limit is f of x is, the limit of f of x is 1.775 as x approaches 0.5. What I want to try to do is show that for any of these epsilons I can pick, and notice my epsilons are getting smaller, I can find a delta so that whenever x is within a delta range from c, 0.5, then the f of x is within the epsilon range. That's not making much sense. Let me put it onto the graph here. So here's my graph, and I wanted to start with epsilon equals 1, and I want to slide my deltas. Right now, what is going on? Okay, so when I slide my epsilons around, that changes this band around that's centered on what I think is the limit, 1.775. So that's in the middle. And my delta is closing in around 0.5 right there, where I'm looking for the x is getting close to that. And so the idea is when I've got delta equal to 1, there are x values where inside this red delta band, there are x values where the y value is outside of the blue epsilon band. So that's a problem, because I want to say whenever x is within this delta band, the y values are always in the epsilon band around the limit. So I'm going to slide this delta and make it smaller until I get, oh, there it is, it turned green. So now whenever x is in any of these values here, the y values that match up with it are all within the epsilon band. So when epsilon was 1, a delta of 0.65 works for me. And so I'm going to put a delta of 0.65 works there. Now I'm going to try another epsilon. I'm going to try a smaller epsilon, maybe 0.5. And now notice the delta doesn't work here. There's some of these values where the x value is within delta of the c value, but the y value are not. So I'm going to shrink this down until I get it. Okay, now they're all inside. So that was a delta of 0.39. Smaller deltas would work as well, but I'm trying to find maybe the biggest possible one that would work. So delta of 0.39. 0.39. Okay. Now I want to try a smaller epsilon of 0.25. And notice the delta I had before doesn't work, so I'm going to shrink that down. Okay, there it worked, 0.22. 0.22. Now I want to try a smaller epsilon, 0.1. So 0.1. Notice this delta doesn't work, but I can get a smaller one that does. Great. 0.1. So the idea is, could I keep picking smaller and smaller epsilons, and whenever I have an epsilon, can I find a delta? If I can always do that, we say the limit is that number. So let me just pick a little bit smaller, say 0.01, and see if I can find a delta. Yep, it looks like 0.01 works for that. So I could even get smaller and smaller and smaller. So that's the idea behind this. Let's look at another function. Here's the function. It's a piecewise function that says f of x is x cubed whenever x is not 7/10, and f of x is 1 when x is 7/10. And we're looking for the limit as x approaches 7/10. And I've got a list of epsilons I'm trying to try out here. And so this is the function I've got here set up for x equals f of x is x cubed except for at 7/10. So that's right here. I've got an open circle there, and you can't see it because I've got it off the screen. I've got a dot right there. So the limit as x gets close to 7/10 is probably this y value right here, even though that's not a point on the function. And so I'm going to guess that the limit is this 0.343, which is 0.7 cubed, as x's get close to 0.7. So that's my guess. I got the 0.343 by looking at what I thought 0.7 cubed was. I'm going to start with an epsilon of 1 and a delta of, let's see, delta of 0.5 doesn't work there. I need to zoom out a bit. There we go. So I can see here that when I'm 1/2 of a unit away on either side from 0.7, there's some of these that are outside of the epsilon band. So I need to shrink my delta down. There we go. And so I've got that worked. That was delta of 0.4. And when I go to a smaller epsilon of 0.5, let me just type it in. This delta doesn't work. And so I need to go smaller, 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 smaller. There we go. That one worked, 0.24. When I try a smaller epsilon of 0.25, then this delta doesn't work, but I can make a smaller one. Notice that I'm not including the point at 7/10, and that's because I don't care about that one. I just care about getting close to 7/10. So this delta of 0.13 works. And let's try an epsilon of 1/10 and a delta of, there we go, 0.056 works. So whenever the distance between 7/10 and x is less than 0.056, the difference between the y values in there and 0.343 is less than 1/10. 0.056. So the idea is, if I can keep shrinking these epsilons down, can I keep finding other deltas? And the answer here, it looks like, is yes. We can get more formal with this, and I will in another video. That's the basic idea of what we've got. And let me just end here, and then we'll pick up with the next video on some other more complicated versions.